Society of Fire Protection Engineers and Minnesota Fire Protection Council. Our topic tonight regards an introduction to optical flame detection technology and fire testing. Our two representatives are here, Buck Crosley and Ron Gilmore. Before we get into their presentation, I just have a few announcements. Number one, how many have their VCRs rolling tonight? The Society of Fire Protection Engineers have approved the formation of a membership committee. The first meeting is going to be held Monday, May 18th in Cincinnati, Ohio during the NFPA meetings. Unfortunately, they kind of squeezed it in during when a lot of the good NFPA seminars are going to happen. Scott assured me that he was going to be there when it happened. By the way, Scott Cottrell, past president of our chapter, is going to be attending the NFPA meetings and also will be attending the SFPE meetings this year because can't make it. He's got me too busy right now too. So if anybody's interested, I have a couple telephone numbers and some other information to call if they're interested in attending this meeting. So we got this up here right here. Fire Protection Connection is a little advertising rag that's published by a private group, and what they do is advertise for helpful audience in our industry. If anybody's interested, either getting copies monthly of their newsletter or advertising in it. I've got information up there too. If somebody's looking for design professionals or you're putting yourself on the market. Minnesota Department of Public Safety, the Fire Marshal's Office. They want me to share this information with everyone, and you may have received a copy of this already in the mail. The Fire Marshal's Office is in the process of adopting an updated edition of MUFC, the Minnesota Uniform Fire Code. Right now, the 1998 MUFC adopts by reference the 1996 edition of NFPA Standard Number 13, Installation Sprinkler Systems. All systems designed after the effective date must be in accordance with that standard. I was saying between now and the effective date, designers have the option of designing to either edition of NFPA 13, the current or the new 96 edition. Whatever edition is used, however, must be used in its entirety. The contractors are not allowed, or design professionals, not allowed to pick and choose certain sections of each one to best fit their needs. So if anybody has any other questions on that, I have some information right here, or they can contact John Neschip or Dave Ritter. The second conference on fire safety design in the 21st century is being held at Worcester Polytechnical Institute in Worcester, Massachusetts, June 9th through 11th, 1999. The goal of this conference is to help define a roadmap for advancing implementation of modern fire safety design practices. And this is a follow-up to the first conference on fire design and safety that was held originally in 1991. So if anybody's interested in going to this conference or submitting abstracts for this conference, please see me. I've got the information on that. I have a copy that was given to me, the Code of Ethics for Engineers. If anybody's never or ever had a chance to read this, it's a real interesting read, just to see what the job of design professionals, I guess, are in the perfect world, or the ideal world. If anybody would ever like a copy of this, or would like to read this, just for the read's sake, let me know. Get them a copy. If anybody's NICET certified right now, probably get the newsletters. NICET's on the internet, www.nicet.org. I don't know which server org is, so they don't have an email address, but this is their website. If anybody needs any more information on the newsletter. This year, they're providing the SFPE annual and Senate meetings on Sunday, May 17th. All SFPE members are welcome to attend, and they encourage us to invite our chapter members, as well as extra registration forms are enclosed in this mailer I got. They're going to have an ice cream social that day in Cincinnati. And Scott, are you going to be at that one too? Well, let us in on what the ice cream really is.
Ice cream social was a Billy bar. And if it says it's at 4 o'clock, if you're not there by 3:30, you don't get a Billy bar, so.
By experience, you know that, right?
It's right. University of Minnesota has a 3-day seminar on network security, July 21st through 23rd. If you're really into computer systems and into network systems, this is a seminar to go to. They've mailed me brochures and information if anybody's interested. Please see me after the meeting. Like that, University of Minnesota also publishes an information technology programs booklet for adult learners about different programs that has to offer. So if anybody has any questions or wants any information on these programs, see me. Oh, I see. Real quick, this one is done. 1991, as SFPE published the first white paper in the Society's perspectives on the roles of the engineer and the technician in the fire protection system design process. The revised white paper was approved at the Board of Directors meeting on March 17th of this year. The white paper states that SFPE recognizes that defining fire protection system design and layout in terms of the roles and responsibilities of engineers and technicians sensitive undertaking. The engineers or technicians overstep their roles if they participate in aspects of design for which they are not qualified by education, training, or knowledge. This revised white paper explains the relative roles of those who contribute to public safety, including engineers and technicians. Copies of the white paper will be available at the SFPE meeting from the headquarters. If anybody needs any more information on this,
Certainly a paper that everybody in this room, whether you're a contractor, engineer, a designer, whoever is involved in the licensing or as a registered professional needs to read, because it is a position that the SFPE has taken, and it's being used by many of, or apparently will be used by many of the boards of registration as they start deciding who's going to be doing what. So it is, I'd say, required reading for most everybody that's going to be, or has been, will be, or is going to be involved in the licensing or design versus professional engineer debate. Pretty well worth getting a copy of that, and you can get it from the SFPE.
Michael Harrow, who's our liaison to the Governor's Council, informed me that there's a task group formed on this very topic. The task group is going to look at who should design sprinkler systems, either or NICET technicians or professional engineers. If anybody has any questions in regards to some input to this, they should call Michael Harrow amongst their enterprises. 851-3085 for that information. Also, the 1997 UFC Uniform Fire Code will probably be adopted this June also. It's going to affect age occupancy and educational buildings and also fire alarm systems. Right now, the building code division here in the state, and they're presently wrestling, as a matter of fact, they're auditing right now to see if the building code division should be in the Department of Public Safety or exactly its role in the state should be. And either Michael Harrow or Tony Martino, who's Mike's alternate, will be able to answer my questions on this. And last thing I have is that in the Fire Protection Contractor magazine, there's a quote in here, and I can't find what month is this that I'm going to find who said this quote. It says, sprinklers are a necessary product. They're not easy to find and they cost a lot of money. This looks like a good business to get into. So as soon as I find out who had that quote, I'll get that to my head, probably in September. But this time I'd like to introduce our two gentlemen who's going to be giving us a real quick education here. Who's going to go first, Bob?
Yep. Yep.
Or Gilmore? Bob is a senior flame product specialist, and Rob is the flame engineering manager with Detector Electronics. And I guess I'm going to get on the podium here and let these gentlemen do on the program. But one last item before we start, okay? And we haven't done this in a while. I'd like you to know, if you haven't met our members, I'd like to begin with standing up at this table right here. Katie, if you want to start, we're going to really quick introduce ourselves.
Katie Bjorgi, Cornell Fire.
Avery Reese, Cornell Fire.
Hi, I expect performance from company.
Max Wilson, Renault Fire.
Jason from Katie Johnson.
Jim Temple, Windows Fire Protection. Dave Marshall, Fire Protection Design Services.
Tom Miller, Renault Fire.
Bob McCallum, Skyline Fire Protection.
Shasha Bajua, ASC Fire Protection.
Sanj Navade, ASC Fire Protection.
David Woolley, Newman Companies. Sam Navadi, ASC Fire Protection.
Hi, I'm Matt Frost. I'm the Detector Electronics rep. I work for a company called Process Instruments.
Chris Willems, Future Fire.
I'm Kirby Kiefer, State Firefighter Training.
Jack Patel from Trail Fire Consultants Incorporated. Paul Water. Bill Hawker, ditto.
My name is Paul Crosley, and basically what I do is the marketing and product planning for our flame detectors. And it's kind of an exciting product because they're very fast. They can do a lot of things you'll see tonight. What we plan to do is I'm going to show a video while we're eating dinner, and it'll basically show the products. I'm going to go over just a brief overview of principles, and then we're going to go down from here to our test site where we actually do all our fire testing on our products. And you'll actually see the different technologies work. You'll see the limitations. You'll see advantages, which will help you decide which is the right product to use when you have to use a flame detector. And you look at it, flame detectors is one piece of the whole puzzle. You have the sprinkler, water, foam, the whole thing, and it all gets wrapped up by you guys. We just try to supply the best possible detector we can to help you guys along and keep you out of problems. But why don't we grab our food? Is that how you normally do it?
We can do this.
Why don't we grab the food, and I'll start the video after everyone sits down. And I'm going to set a handout if you want to put it underneath your plate or whatever, grab it. And this is what we're going to be going over, and you can use it for reference. Okay, as you guys are eating, I'm going to turn on. This is a videotape showing our products. It actually shows our test site where we're going to go after our little presentation, and you'll actually see these products work. This video is slightly dated. You're going to see some technology that we've improved upon. It'll be the old technology video, but you'll see the improvements at the test site tonight. Just this kind of goes over the fundamentals, and if you'd like, we can supply you guys with the tape. If you'd like, I think I have some for all of you, but we can provide that.
Yeah. Any tapes, if you see anything, you need any tapes, any literature, let us know. So gladly supply that to you.
Systems is pleased to present the Detronix Flame Detector Selection
Is that
Guide.
loud enough? Everybody here?
Detronix tests the strengths and limitations of various detectors at its fire test facility. Tests have been conducted on unique fuels, difficult applications, harsh environments, and false alarm resistance. Detronix has developed specialized hardware and software to produce its exclusive data acquisition system, which records these tests for analysis. This presentation will feature 3 detectors: an ultraviolet, a single-frequency infrared, and an ultraviolet-infrared combination detector. Each of these detectors is solar blind, available in both controller-based or unitized configurations. A series of tests will be performed to demonstrate each detector's strengths and limitations. The ultraviolet detector is a good general-purpose device because it has few naturally occurring false alarm sources. The UV detector senses radiation between 1850 and 2450 angstroms. Virtually all fires emit radiation in that spectral range. Single-frequency IR detectors are useful in many areas where UV detection is not appropriate. They use a patented, narrow bandpass optical filter sensitive to radiation in the 4.4 micron range, an important wave length for hydrocarbon fire emissions. They also use a flicker frequency to distinguish between hot body radiation and actual fires. Typical response times are around 3 seconds. UV-IR detectors consist of an ultraviolet and an infrared sensor paired together. The UV-IR detector is very resistant to false alarms because both UV and IR sensors must respond before an alarm is given. And while both UV and IR detectors have false alarm sources, they have virtually none in common. Typical response times are between 1 and 5 seconds. All of the detectors have a cone of vision of approximately 90 degrees. Since the detectors will not see fires outside of this cone, careful aiming of them allows a friendly fire, such as a flare stack at a refinery, to be present in the area without triggering an alarm from the detectors. However, mounting detectors in the corners of a room at 45-degree angles makes it possible to provide thorough coverage of everything in the area. The first fire test will demonstrate speed of response to a 1 square foot gasoline fire at 40 feet. In applications with very hazardous materials, speed of response can be the most important factor in choosing a flame detector. The UV detector responds fastest because it only requires the fire to reach a certain intensity before sounding an alarm. Although the vast majority of fires are hydrocarbon fires, some applications have unusual fuels. In those cases, the ability to see non-hydrocarbon fires is important. An example is a hydrogen fire at 40 feet. The UV detectors saw the hydrogen fire while the others did not. This is because non-hydrocarbon fires, such as hydrogen, ammonia, titanium, and magnesium, do not emit radiation in the 4.4 micron range required by the IR and UV-IR detector. The next fire will be a methane plume fire, as defined in standard 3260 by Factory Mutual, observed at 40 feet. All detectors responded well to the fire. Unlike the plume fire, some fires from gas leaks are under high pressure and can be quite large. A major gas company conducted high-pressure gas fire tests on Detronix flame detectors. These tests were representative of risks found in industrial applications. The flames produced in these tests are readily detected by Detronix UV, IR, and UV-IR detectors. The ability to reject false alarms is an important criteria for a flame detector. A common false alarm source in industrial applications is arc welding, here observed at 40 feet. The UV detector has responded to the arc welding, while the others responded only to the fire. Arc welding is an intense emitter of UV radiation, but does not emit in the 4.4 micron range. Therefore, the IR and UV-IR detectors do not respond. The ability to ignore arc welding while responding to the fire it can cause is an important capability of Detronix UV-IR and IR detectors. Welding is a high fire risk activity. In America, between 1981 and 1985, welding caused over 3,000 fires each year, causing damage of almost $40 million each year. Flickering hot body radiation is another common false alarm source. Common sources of this radiation include hot engines, manifolds, or lights, interrupted by moving machinery or people. The single-frequency IR detector has responded to the flickering hot body radiation at a distance of 30 feet. The UV and UV-IR detectors do not, because hot body radiation does not affect UV detectors. Some environments have conditions that could blind optical detectors. Common blinding elements include oil, dirt, mud, grease, and smoke. The detectors are 40 feet from the fire. The single-frequency IR detector responded, but the UV and UV-IR detectors were blinded by the oil. Infrared detectors have a high tolerance to these optical contaminants. Some vapors can also blind UV and UV-IR detectors by absorbing UV radiation before it reaches the detector. Use careful consideration before selecting a UV or UV-IR detector to monitor an area where these agents are common. Another possible blinding source is from ice and water films, especially in outside applications. Ice storms or salt sea environments are examples of these conditions. Water and ice absorb IR radiation and blind IR and UV-IR detectors. The UV detector is less affected by the ice. All Detronics detectors are available with optical integrity, which automatically checks the electronics and optical surfaces of the detector. In this case, the IR detector is blinded by ice, senses that it is blind, and gives a false output. Even in areas without optical contamination, optical integrity is valuable because it checks the electronics of the entire detector and warns of any developing fault. To summarize these tests, the following 4 questions should be asked concerning flame detector selection. First, which detector will see the fire that is likely to occur? If it is a non-hydrocarbon fire, a UV detector is the best choice. Second, which detector will respond to the false alarm sources at the application? The selection of the best detector depends on which false alarm sources are likely to occur. Third, which detector may be blinded by the optical contamination that will exist at the application? The selection of the best detector depends on the contaminants at each application. And fourth, how fast must the detector respond to the hazard at the application? Some applications have fuels that must be extinguished in milliseconds to avoid disaster. Other fuels burn more slowly, and false alarm sources or optical contamination are a more important consideration. The UV detector is the fastest and least expensive of the detectors. It can see almost all fires. It can be used in any application that does not have welding, nuclear radiation, or dirty environments. The single-frequency IR detector is best used in dirty environments or where arc welding is used. Good applications of single-frequency IR detectors include offshore platforms. The UV-IR detector resists false alarms and has a good detection range. It will see fire even in the presence of welding. Good applications for UV-IR detectors include aircraft hangars, transport loading racks, and compressor stations. There is no perfect fire detector. Each has strengths and limitations that make them appropriate in some areas and less appropriate in others. As an industry leader, you can count on Detronics to give you the complete story on every kind of optical flame detection available. The reason is simple. We sell them all. So when you need reliable detection, be sure to consult us, because even though there is no perfect detector, we have the right detector to meet your needs. We are Detector Electronics Corporation. For more information, contact us or a sales representative near you.
Didn't hear any snoring. It's a plus. One thing I did start with is that this is where basically Detector Electronics home office here. We have offices in the UK, Singapore, but we design, build, and do most of our cellular product right from this building here. And we are the world's largest producer of optical flame detectors, and we offer technology that is second to none. No one really can quite compare. Now, how many people here have actually used a flame detector before? I know it's pretty good. Flame detectors typically work very well where other technologies don't work very well. You guys use a lot of smoke detection.
Obviously, you can't use smoke detectors outside, they just don't hold up, won't give you a reliable alarm. This is where flame detectors really came into use, because there was applications where they're hazards, can't be protected with smoke detectors. Can't have a guy watching it all the time where it's very fast and the guy's seeing it, he's gonna run away before he does anything anyways, because it's so bad. And places like munition plants and oil platforms, you really can't get away fast enough, you don't have a way to get off. And so optical flame detection really grew from these hazardous areas. Can everyone see this? All this information right here is also in your handout. When we look at optical flame detectors, we're looking for the visible, the ultraviolet or infrared energy that's coming from the fire. If the fire was smoldering, we wouldn't be able to see it because it's not giving off the right properties. So we're actually looking for, after the flames have grown from the product, and looking for the energy level to be at a required level. If we look at this application here, you're looking at a plane. We have optical flame detectors looking from either side. They can be looking from the front. We have systems that are designed to act as one controllable systems, or have unitized products that can be tied into any existing fire panel, giving you a lot of flexibility. When we look at a flame detector, one of the key items is that the cone of vision. Where does the detector actually see, and then how do you use that to cover a complete area? When we look at a flame detector, we have a typical cone of vision of 90 degrees, and we look at Factory Mutual, tells us that typically, or minimum, at 50% off the central axis is where your cone of vision at 45 off angle is drawn. We have made some changes recently with the new product, and we actually could push that product up to 75% of the detection range, giving you more coverage per detector. Allows you to zone detectors, cover areas where you may be forced to rely on a single detector. And we will be showing detectors today on access, but the response can be figured off at 50% for some, 75% on a single product. One of the key features in optical flame detectors, it has to know that it can see a fire. And Detector Electronics was the innovator of optical integrity, or basically an optical check on the detector. And we look at the detector, and this is incorporated in all our detectors. We have a UV source that is bounced off a reflector through the window, back through the window to the detector. And that verifies that that detector is capable of seeing a fire, or if it's been contaminated and no longer is able to see a fire. It'll give you a fault, telling you to either clean it, service it. It allows you to rely on your detector to be in service when it's out there running in the outdoor environments. We have an infrared detector that also incorporates a very similar, except we now have an infrared source that comes off a reflector back to the sensor. In both these optical check methods, we're looking for the radiation in the wavelength that the detector is looking at. So we're verifying the window's clean, and we're verifying that also the detector is capable of responding to radiation in the proper wavelength. Very reliable. We look at the different technologies. We really started with Detector Electronics was ultraviolet detectors. They were very good, general duty, but we found that there's a lot of areas where there's welding, a lot of areas where there's radiation. People looking at the integrity of pipelines. They do a lot of X-ray. And UV detectors are very good at telling you when you're doing that. So we incorporated an infrared sensor with it, and we also built a single frequency infrared standalone for use for very dirty areas. Since then, we have added a dual spectrum, which is a dual wavelength detector, looking at two different wavelengths. And this is our new multi-spectrum IR detector, which gives us an advantage for long range and also high false alarm immunity. We look at just a few concepts
We're going to be showing today the black body, which was the heater you saw in the video, which is something that is normally in an environment, and we'll see what effect that has on flame detectors. The other key item here is that flame detectors are governed by the inverse squared law, which basically says to double your distance, you have to have your fire size grow by 4 times. So when you look at the detection range of a product, you have to look at what size fire you can live with and size the detector to the distance to the fire size so that you don't rely on a 10-foot fire in a 20-foot building. The flame detector is going to be able to see it, but you may not be able to save anything once that happens. We're going to be showing it down there is also StarLogic, which is a selectable transient arc rejection. We use that on our UV and UVIR detectors, and also a patented TDSA, which is time domain signal analysis. And this allows a IR detector to respond to fires very fast, but reject regularly modulated IR, which normally would cause a false alarm in that type of technology. We look at ultraviolet detector. Great, it's general duty. It can basically see every kind of fire you can do. It can be very, very fast. It's solar insensitive. Limitations, as we said, welding, very, very bad. You think of a guy working on a pipe a mile away. If that detector is in that direction, it could detect that welding a mile away, and that could cause a false alarm from a facility that you don't realize that they're welding. The other item is X-raying, and X-raying is hard to control because a lot of people think that the wall's going to stop it. We have compressor modules up in Alaska where they're X-raying the pipes, and all the detectors go off inside. Can't figure out. So what we've done is gone with different technologies to handle problems that UV can't overcome. When we look at single frequency infrared detection, it is very strong because it can run in a very dirty environment. It doesn't need a lot of maintenance. If there's oils present, it's basically invisible for an IR detector. IR detection is basically to arc welding unless you get very, very close. We look at a detection range for someone arc welding at about 15 feet when the detector is set at its highest sensitivity as compared to a UV detector at a mile or more. It's fairly insensitive to it. We do offer a high-speed version for special applications such as high-pressure gas lines, but there are some limitations with IR. And as we saw in the video, we look at 4.4 as our peak wavelength on IR. Non-carbonaceous or non-hydrocarbon fires cannot be detected by that because they don't exhibit any kind of radiation in that area. So we have to really stick with like your petroleum products. It will not be able to detect something like silane. It will not be able to detect hydrogen. So you have to know what you're going to detect and then fit the right detector to it. And the TSA, if you're using a detector that doesn't have that, modulated IR, like a generator looking through the fan blade, could cause a false alarm. We incorporate the two technologies, the strengths that you get with an ultraviolet and the strengths you get with the infrared, and we join them together for our UVIR. Two standalone technologies joined together. And we benefit with this is that now we don't have problems with welding, but we still have, we can't see non-hydrocarbon fires, and the device now is slowed down slightly more. We have a response time of about a half a second, and we are insensitive now to welding at 15 feet or greater. And we will be demonstrating this so you'll actually be able to see it. We look at multi-spectrum infrared detection. We have dual spectrum where we use 2 different infrared sensors, and we have dual where we use 3. What is really great about a multi-spectrum infrared detector is that we can increase the false alarm immunity to just virtually anything. It's very hard to fool. We also gain, on some models, very, very fast, 6 milliseconds. We can approach the speed that a UV detector could, and we don't suffer the trade-offs of having false alarms from welding, lightning, and other sources. We gain long range with this type of technology because it's using ratios, using less signal. And we also have fiber optic coupled detectors that are, it's a product that we use for automotive applications where basically a conventional size detector can't fit, but they're also very false alarm immune. We do have, when you look at multi-spectrum, is that you become more fuel specific. We have to look at what fuels you're using and again, size it correctly. It's always important, like we saw in the video, you have to really have a performance spec established for what you want to see, or you can't guarantee that you're going to be able to detect it. Just to go back over, when we look at the ultraviolet, we look at a very, very small area. We're in 1850 to 2450. It's a very narrow section of the UV, which keeps us solar insensitive. The sun does not hit, the UV does not hit from the sun because of the ozone and other water molecules. But it's also immune at that wavelengths to fluorescent lights and other things, making it very, very robust. We look at the IR, and this is true for the UV IRs and single frequency IRs. We're looking at this very narrow 4.4, and this is actually a curve of a fire. And we look at a fire will exhibit in the water band about 2.5, and the signal will be absorbed by the environment. And we get this other clear window, and we use this little sliver here because of the solar insensitivity for the IR in that range. But it also gives us a lot more area to work with, a lot more signal, allowing us to get very good range and reliable detection. We have this is our dual spectrum product, and which is unique on this is that we now are looking at basically a light channel. It's using about 1 micron, looking for the light energy, the ignition kind of a fire, and the heat level of the fire. And this would be at the, well, this shows 5, but typically about 10 to 15 microns. And we look at, here's a portrait of a fire, here's that CO2 emission band right here, which is, we look at the 4.4 on the single frequency, and you see the curve back down here as it's absorbed in the environment. We look at something like a heater. We see we have a lot of energy out here in the farther IR, but it drops off fairly fast in the light range. So basically, it's immune to that type of false alarm sources. The dual spectrum will offer a very, very rugged welding immune detector that can be used in areas where conventional detectors can't be used. We've used this type of product in battery manufacturing, where you have sparks and you have heat baths, where a UVIR would go on the alarm because you have both sources there. This technology allows us to override the problems of other technologies. When we look at just an application here is a refinery, obviously engulfed in fire. This is what we want to basically stop before it gets that big. And you look at our flame detectors are gauged by what Factory Mutual 3260 tests them to. We look at a 1 square foot gasoline fire or a 30-inch methane plume and other fuel 1 square foot fires as our test fires. And I can tell you that there's not a product in the marketplace that can detect fire faster, more reliably, and give you the false alarm immunity that we're going to show you today. We're going out to, let's say, Rob's land. Now, I think it's probably better to see the products work, and then we'll have our own questions after that, because if there's a question that you maybe want to see, we can probably demonstrate it with a detector if we have to. And I don't know if you guys grab my cards. If you have any questions on applications of the technology, give me a call, or any of our inside salespeople can help you with possible applications. And flame detectors excel in areas where just other technologies don't work or are unreliable. And it allows you to cover a large area with a moderate price. I can say the flame detectors are not as economical as smoke detectors, but they sure are durable. We have units that are still running out there that were installed in the early 70s. So they run. So, Are you gonna lead the pack down there, Rob, or are you gonna do it, Matt?
Well, what I'm gonna do is I'm gonna grab the screen here, because I thought it'd be best if we could put our results on overheads.
Did you grab an overhead already?
Yeah, we're all set for that. And, why don't you give me the screen in a couple of seconds?
We also have various, or you can call in here, Detronics Fire Test Facility. This is where it all happens. We use this facility for engineering research and development. We also use this facility for verifying the items that we produce every day in our factory. And I was saying before that each and every one of the IR detectors that we make, whether it's used in a single wavelength infrared detector or a combination infrared UV detector, each individual device is brought down here and subjected to a battery of 9 fires, 3 different fuels to ensure that they perform according to their specification. And that's something that's unique to our company. And UV detectors too receive a fire test, but that's done at the main building. It doesn't need to be quite so elaborate to accomplish the goal. You'll see as we go on tonight why an IR detector, being less easily fooled, needs a more realistic test source in order to determine its level of performance. I was just going over what we have today on the card. What we've done here is to put a sampling of each type of technology here. As our video explained, these are available in controller-based, where the alarm relay actions and the signal processing takes place back at the control panel. Unitized, where it all happens in one device. Either way, the technology is the same, and so what we have here is just a mix of the kinds of detectors that we offer, and the kinds of detectors that are brought to bear as optical flame detectors on hazardous. The X3300 is our newest offering. It's a multi-wavelength device. This allows us to, as Buck was explaining earlier, provide maximum false alarm immunity with the highest level of flame detection sensitivity, leading to greater detection range or more sensitivity to less fire, enabling you to catch a hazard earlier in its occurrence and providing better performance in that way. Here we go on with that one. Oh yeah, this is also, we deliberately put heated optics into this device. This allows us to resist the blinding that we talked about in the video that can occur from ice buildup and so forth. In fact, if you feel this thing, it's running noticeably warm, about 20 C. Nice bath water, 20 C temperature rise above ambient, and that works to a high level of advantage there. We have 2 UV detectors. This happens to be our 7602E. They all have difficult numerical names to remember. The reason there's 2 here is that one incorporates the STAR logic that we saw in the video, which is an advanced signal processing algorithm, and one does not. And we'll be able to, we have with both detectors here, we can show you the difference in performance that allows us to achieve. Here we have the U7698E, which is a single wavelength infrared detector. These have but one IR detector per device, looking at the 4.4 micron region that we showed in the presentation earlier. And again, there's 2, because we're going to be able to show with them the difference between the standard signal processing algorithm, which looks for the occurrence of flicker and the level of intensity, and the TDSA, time domain signal analysis program, that allows us to do some greater signal processing and make some greater distinctions between fire and non-fire sources of infrared radiation. Last but by no means least, we have 2 samples of our UV-IR detectors. This happens to be a unitized device, the 7652, whereas this is a controller-based device. The reason there's 2 of these devices here, primarily so that I can utilize the ability of the detectors with controller-based connections. I can take and look at the individual signal strengths in the IR and the UV detector, and that will allow us to compare the UV and IR outputs of the various fuels. Because another thing we'll see tonight as we go on is that a fire is not just a fire. I'm sure just as it makes a difference in terms of how you site sprinklers and
so forth, the fire hazard itself also makes a difference in terms of what kind of performance you can expect from your optical flame detectors. So that's the cast of characters. The whole thing is, as you saw in the video, connected up to our data acquisition system, which is operated by Jeff. Each device is monitored by the data acquisition system, and the alarm relay is pulled every 10th of a second. We can go faster than that. Tonight's demonstration will be looking at that every 10th of a second. And we also have the detector down at the far end of the building, right next to the fire pan, that we call our time zero detector. That provides us with an automatic means of determining the point of ignition. We've got that set at a very high sensitivity level, and being right up against the fire will produce a response time of about 50 milliseconds, thus giving us an automatic indication of the point of alarm. We can wander over here and take a better look at how this all works. And the interconnection, of course, requires these cables to be present, so please watch the footing. I guess while I'm talking about safety-related issues, I should mention a couple other things. One is that we hope, of course, this is just a nice, calm, routine fire test demonstration, but if there were to be some problem, the exits are to the front where you came in, or to the rear behind Jeff there, and if anything were to happen, please ensure that you're out the door before Jeff and I exit also. There'd be no need to run over here. That's part of the advantage of having your test facility in a World War II vintage Quonset.
They don't have sprinkler system here?
Nope. You think it would warrant it? I don't know. What I wanted to show you here is the data acquisition system and how it operates. And it's a little difficult as we're doing the test, for everyone to see what's taking place. As you can see, the acquisition system runs on an independent time base, scrolling by, and as I say, our sample time is every 10th of a second. The green characters here are hash marks when the detector in question, each column is the detection system in question. And when that goes from a hash mark to a dot, Jeff, can you give time zero some radiation there and demonstrate that? That indicates an alarm. Notice over here we start to see numbers popping up in the yellow column, and that's the count per second. The UV and IR detectors that we're monitoring the individual signal strengths from produce a frequency output proportional to the intensity of the radiation being received, and that is in a unit that we call counts per second. So it's a number of pulses received in a unit amount of time, and that gives us an indication of the amount of signal strength that we have either in the UV or the IR bands. So when we do a response time determination, the point at which the time zero detector trips is compared to the point at which each of the detectors under test indicate their alarm, and the net difference is then the response time. We also have the ability to go in and take a look at the signal level at any point in time in the UV and the IR bands. And you'll notice that our IR detector produces a constant level of output that's used to verify on a routine basis, and it's an electronic zero, and that the presence of that indicates to the controller that the detector is in fact there. Of course, it does not accomplish the through-the-lens check that the OI system does. It's kind of a belt and suspenders approach there. Yep, I'm about ready to get to that. Because not everybody can watch that, we have every system under test today on the enunciation panel board. You'll see them labeled by model type and also by technology. So going from the left side top, you've got 7409 UVIR, that's that controller-based system I showed you. UV system without star. Next down, the UV system with star lock. The 7698E single wavelength infrared detector operating without TDSA. The single wavelength IR detector operating with TDSA. Moving into the next column over, we have the U7652 UVIR detector. It's the unitized package. The X3300 multi-wavelength IR detector. And last but by no means least, and I guess I didn't mention it, although Carter pointed out, is the PM6M dual wavelength detector. And to the left of each one of those tidal blocks then is a red light that will come on indicating when the system is in alarm. Now, with the group of this size, can't see through you. Somebody asked earlier about the implications of obstructions on performance of optical flame detectors. The performance of optical flame detectors is affected by obstructions just like your eyes. If you get something in the way, you can't see as well, if at all. So what I'm going to ask that you do is maybe crowd around towards the edges with some chairs if you care to fire, and the size is 2 foot by 2 foot. Have the detection systems positioned at a distance of approximately 100 feet from the fire. And this is a size of fire, type of fire, and a range that all the detection systems in question should be able to react to. And I thought that would be a good place to start. Everybody ready? Stand, please. Power of that fire. You can actually feel the radiant energy on your face. Quite an intense fire, and I will ask Jeff to put it out before it gets carried away with itself. Do not try this at home.
Board lit up like a Christmas tree here.
It does do that. We'll get to individual response times here.
Well, that 2 foot by 2 foot fire would be a typical hangar fire size that they would typically test for at 100 feet. When you go out to 150 feet, their test fires have been up to 10 by 10. Or 100 square feet, so very huge fires that Rob got to have fun with.
We could do that fire here
That's just regular
once.
That's just regular gas. But we have the ability with all those detectors are actually say 3 by 3, so much smaller fire than actually is specified for, and that gives us the reliability. You know you're going to be able to detect it when you need it.
Okay, bright light warning to those of you standing close to the. This is pretty typical of what you might see here from the detectors in question. You see that we had alarms ranging anywhere from under a second to just over 10 seconds. Our UVIR system operated in 5.2 seconds. UV systems, depending on their sensitivity level and whether they use the star logic or not, 0.9 to 2.8 seconds. The single wavelength IR, 7.2, 11.6 seconds. Again, this unitized viewer went in 3.5 seconds, the X3300 in 4.6 seconds, and the PM6M in 6.1 seconds. You might wonder why some of these detection systems took as long as they did to react, and it has to do with the fact that this is their rated maximum detection distance. And also the fact that, believe it or not, even though to our eye it appears that this fire develops virtually instantaneously, that it actually takes a certain amount of time for the fire to come to an equilibrium condition and reach its peak size. And I can illustrate that by taking a look at the count per second data that we get from the fire. To do that, I have to go back into the data file, determine when the start of the fire was, and I'll take and look at the first 5 seconds and then 10 seconds later.
keystrokes, Rob.
Well, you know, sometimes there's an operator error from time to time. I won't try to hide that. Okay, so here's the UV and IR outputs we're monitoring from the detectors in that first 5 seconds of the fire. And while that's coming up, I'll prepare sample seconds later.
So our next fire is going to be a 1x1 gas main at the same range. You'll see a difference in response.
During this pause, I'm going to excuse myself. Scott Petrell, our past president, is going to adjourn the meeting when we're done. I have to be somewhere in half an hour, so I'll have to excuse myself. I want to thank everybody for coming out. I want to thank our presenters too. I do have your business cards, and we will be contacting you because we will be presenting you with a complimentary S&P coffee mug that we have too. They're nice, they're black and gold,
Great.
or a beverage mug if you don't drink coffee. So I'll be in contact with you gentlemen, so I have to excuse myself. But thanks anyway, and like I said, Scott will adjourn the meeting. Our next meeting will be in September. It will probably be the last Wednesday of September this fall. There will be a newsletter out in the don't snicker when I say that. Scott, when he was president, was very good about getting the newsletters out quarterly. I've been a little tardy on it.
Some of you are volunteer.
We're always advertising for an editor and all too. So thanks again, everybody. I'll see everybody either around town or in the fall.
Thanks very much.
You gotta take the same route back to get here.
I compliment them. If you end up in Iowa, you're taking the wrong turn. There's no doubt. Okay, I should say from the outset here that the UV and IR counts per second are not necessarily related to one another. In other words, it doesn't indicate an equal level of UV to IR. But you can see that our UV output, we're monitoring 3 detectors, somewhere in that 20-25 counts per second range. The IR detector is in the 29 count per second range, and you may remember that the response time here was somewhere in the 5-second range. Over this first 5 seconds average, we only had 30 counts per second, and actually the controller is looking for in the neighborhood of 35, explaining why it would have taken that long for the system to alarm. As I said before, believe it or not, fire takes a little while to reach its equilibrium point. Here's a snapshot that starts with 10 seconds after ignition. Here's a 5-second sample period for the average. And notice how everything's grown. Basically almost doubled in each category. UV now is up to 41 counts per second. IR is at 55.7 counts per second. And again, when you're looking at the response time of the detection system, it's pretty typical for some manufacturers to use a method that we call the shutter method, where the fire is lit, let the thing get cooking real good and hot, maybe for 15 seconds, even 30 seconds. Then the shutter is pulled away and a response time is taken with that method. Of course, that isn't really typical of what you're going to see in a real fire detection situation. And although we may resort to that when it's a competitive situation, that's the way the customer wants to run the test. We like to know how we're going to perform through natural ignition. And I point out, as we now switch to the 1-square foot pins you saw in the video, all these hoses and all this jazz coming, going into the floor drain and what have you, all that is geared at one thing, and that is to keep the fuel temperature, as we do one test after another, and we ignite each fire at room temperature. Because again, if the fuel's hotter, you get a different ignition characteristic, a more rapid response time, and from the standpoint of trying to use a fire as a quality check, you'd be measuring the variability of the fire and not anything significant with respect to the performance of the detector in question. Okay, we'll refer back to these test results now that we're going to go to a fire that's 4 times smaller, a 1-square foot gasoline fire, and you may have noticed that, or actually, you didn't slide. each time we burn a gasoline fire, it's important to recognize that gasoline is not a pure compound. It's a mixture of compounds, some of which are quite volatile, some of which are less volatile. And we start with new fuel each time we do this because, again, what's the actual hazard? Isn't it going to be fresh gasoline, or is it going to be heated gasoline? And again, you can play games with this, but it's important to be aware of the issues so that you're not fooled into thinking performance is what it may not actually be. We'll do the test the very same way, and I believe everybody's ready. That's about all I expect to see happen. Those two detectors, Gilmore alarm. All the other detectors are out of range.
We're going to move into row.
50 feet. Thank you. It's a latching output. That particular detector is an intrinsically safe device. You don't have the ability to select a latching output or an output that persists until you reset by cycling power. So it's not still an alarm. The alarm relay is a latch type output, much like a smoke detector can be latched in the 6M and the X3300 are the only detectors rated to see this fire at this distance. And even though it may be rather obvious, there sometimes can be confusion about, people may have confusion that, oh, you didn't see this fire, so that means 7602E, for example, can't see a gasoline fire. No, it's not really true. It either has to be bigger or you have to be closer. There was not enough signal level. The criteria was not met in order to generate this an alarm. Let's just compare here we'll just put it up here. Here we have, these are hard to read when you just got transparencies. All right, now here is the count per second output level of the UV and IR detectors, and a lot lower, especially in the UV detector area. You can see basically pretty close to zero. That was compared to our 25 counts per second that we had before. And notice that in that first burst of ignition, the II detector did get some output, but again, it was not anywhere near adequate to generate an alarm. Even if it had been, its UV partners were not up to their output level, which is extended as typical 25 counts per second. Very typical field setting. Okay, and as we saw before, there is some increase over time with this fire, but not as much. And that can be understood in terms of the fact that there's not as much fuel to heat, and a smaller fire does tend to reach equilibrium faster than a larger fire of the same fuel type. I guess one other thing to notice here is what we call the saturation output level of the UV detector. The UV detector can't really put out much more than 800 to 1,000 counts per second, regardless of the intensity of the UV radiation it's receiving. And you'll notice the time zero detector is operating quite near that, being that it's only about a foot from the fire. If at any point there's any questions or any additional interest, please stop me, interrupt me. This is, I've seen this before, so.
Hey, Rob?
Yeah.
With the gasoline here now, do you test with different types? Like if you use unleaded versus aviation fuel, and you see that with your detectors?
We do indeed. In fact, when you may recall some years ago when leaded gasoline became virtually unavailable and unleaded became the standard, not only did we have to do a little research as to whether or not there was a difference, but there was a slight difference, and of course that meant we had to reestablish control limits and so forth for our production tests. It caused us a little bit of grief, but we have, you might notice all the flammable storage lockers around here. Well, it's a virtual cocktail cabinet full of different flammable liquids and materials, because each flammable material, even though they may be of a similar category, will have its own characteristics. For example, in the aviation fuels, there's your avgas, which is pretty similar to gasoline. Your JP4, which is the military fuel, it's gasoline-like, but a little less volatile, takes longer to reach equilibrium, and has its own characteristics, all the way up to the JP5 and JP8 type fuels and the Jet A's, which are much more like kerosene. They don't readily ignite at room temperature with an ordinary ignition source, and each one is different. And one of the benefits of having a facility like this is that we have been able over the years to establish quite a library of the UV and IR characteristics of a number of different fuels. It's not at all uncommon for us to come up against a customer may have a hazard of fuel that we don't have any previous data on, and in that case we can conduct a test so that we can provide guidance as to what type of technology to use, what specific distances and sensitivities to apply to the hazard. And,
Plus it's fun burning.
Yeah.
When you say equilibrium, what does it mean?
What I mean is the point at which the radiant output of the fire reaches a plateau and gets no higher. We saw with the 2x2 gasoline how during that first few seconds of the fire there was a smaller amount of UV and IR radiation than there was 10 seconds later. And typically, I don't have a graph here, but I'll sketch here with my laser. If you can imagine a little XY graph here, we're going to look at over a long period of time the UV and the IR radiation, let's say over a 30-second period, you'd see the level rise and eventually level out, maybe a little bit of oscillation, showing the normal moment-to-moment variation. But what I mean by equilibrium is that point at which you reach basically a plateau.
Regardless of the growth of fire.
In a contained size of fire. An equilibrium point obviously wouldn't be applicable to a fire that was from a spill where the level of fuel kept changing. Spill got bigger and bigger and bigger. That would not reach equilibrium until whatever vessel was draining was completely drained. But in a pan fire like this, where it's a defined size, then an equilibrium point, we can think of an equilibrium point as being a valid concept.
So if it is a growing fire, there could be a potential problem of detecting it. Is that correct? Like say for example, if you have a flammable liquid storage and tank filled, and your fire is growing.
Well, I guess
a threshold, I guess is what he's asking. Is there a threshold above which it's going to alarm anything? You're not exactly what he's asking, that's how I'm thinking about it.
Well, that's exactly right. And what I was trying to illustrate with the two gasoline fires that we had, the square foot and the 2x2 foot fire, is that the fire, you can imagine that kind of simulate small fire in one case. If that then grew to that bigger fire, the 2 foot by 2 foot fire, now it will be detectable at a distance of 100 feet. So there's no special difficulty posed by a growing fire. As a matter of fact, a growing fire will become detectable at a given distance or at a greater distance eventually. In fact, that's a very important thing to think about when you're applying optical flame detection is at what point, if there was to be a growing fire, what rate could you expect the thing to grow, and at what point, what size fire do you want to trigger the alarm on? this last set of tests that we did would illustrate that. If you could tolerate that 2x2 gasoline fire without suffering unacceptable damage in your installation, then the detectors could be placed 100 feet away. If you can't tolerate that level of fire growth prior to signaling the alarm, then we need to move the detectors in closer or utilize a more sensitive technology such as the 3300, the PM6M or something along those lines. I think this point will become clear. We're going to run the gasoline fire once again here, but now at 50 feet. Okay?
This gas is methanol, isn't it? No, we're running methanol.
Well, we can do that first, but I also want to run gas. Do you have methanol in the pan? That's fine. So we're, as I said before when we were talking about the kind of tests we do here for production, with each device produced, we do a gasoline fire, which is representative of a yellow fire, produces a lot of smoke, a methanol fire, which is a very weak fire, a blue fire, and then a methane fire or natural gas fire as an example of gaseous fuel. And what we're going to do here is do all three of those fires here at a distance of 50 feet so we can contrast the UV and IR output level of the three types of fire at a given distance. That will also enable us to contrast what we saw with the two other size fires at 100 feet. Okay, is everybody ready?
Fondue you had.
Yes, it's rarely necessary to shave your wrists in this job.
No, you don't have to. It does it for you.
That's what I'm saying. It's very rarely necessary.
This would be a fire that would be typical, say, on an oil platform where they use methanol as a drying agent, or in other processes where they're using methanol as a washing agent. So this came in what you said. Maximum rate of risk. Maximum rate of risk.
Yeah, we'll just let this sit here. You can see it never really gets any greater than this. And this is what I would call an equilibrium point.
When you look at this type of fire, the methanol fire, you'll notice, like the PM6, this is out of range of that product, and it will not detect this no matter how long you wait. The fire would have to be bigger. And you can't think of just in a time limit, I can wait longer. If that fire is never going to get any bigger, the detector will never see it.
Well, I think we've waited long enough to illustrate that point.
A question came up, how come the PM5 is affecting this fire? This type of fire, when it's detected at 1 foot by 1 foot at 100 feet, out of the range?
Yes, it's beyond its detection range for this particular hazard because it's not the same kind of fire. We'll give you some quantitative data here momentarily.
So we look at different applications, there's different fuels, or actually, which makes it very hard when you talk about solvent storage area. You may have a mixture of all these different fuels, and you'll need to select which is going to be the hardest to detect, and basically base your design off of that lower burning, lower volatile fuel as your hardest to detect, causing your detectors to move in accordingly.
Review the response time results quickly. You saw it for yourself as it happened. We had the things. That's fuzzy. We had, okay, I understand what happened here. Quite a few of these devices went into alarm as we put out the fire. Managed to get a response right at the tail end. Notice the X3200 first to respond. Of course, it being a very sensitive device, one can expect that. Our UVIRs And the single wavelength IR detectors are right just beyond their sensitivity, beyond their detection range, the sensitivity levels that we have them set, or in the case of the fixed sensitivity devices. So again, what I'm trying to say here is that it's not that they can't respond to this methanol fire, but they need to be another 10 foot closer, and they would be able to work just fine. I talked earlier about how we use the count per second data to look at the differences in fuels. We've talked a little bit about that already. And again, I've taken 2 snapshots of the output here. In the first 5 seconds of the fire, very little UV, pretty low levels of IR. A few seconds later, see that the UV's grown a little bit, but not really the alarm point yet. And if I went into the last very end of the fire, finally we did get some alarms in the UV, somewhere in the 25-second range. Let's just compare methanol data to that of the gasoline data. We won't be able to compare absolutes until we run the gasoline at this distance, I guess. So that will be next, right? Gasoline next? Getting ahead of myself. See here, even at the very end of the fire, we finally get to the point where we're up above the alarm thresholds on the IR, and the UV average is quite low, but momentarily, with a very short processing time, at least some of the detectors were able to come into the alarm. Okay, now we're going to keep this up. This is the absolute equilibrium point, and we're going to take now a look at same size fire, but a different fuel, same distance, so all we're changing is the fuel type. Let's look at a square foot of gasoline. Is everybody ready? Okay. Once again, we see range of response times anywhere from 7 seconds. Everything alarmed, some take longer than others. You notice that the U7698E, whether we're running the TDSA algorithm or the standard algorithm, now that they're both within range with this hazard, react to roughly the same amount of time, 3 to 5 seconds. And everything else fell into place along the lines that you would expect. The thing I find a little surprising here is the reaction to 7602 star logic, and maybe the count per second data can shed some light on that. Indeed it does. Okay, now just to compare apples to apples, here's gasoline. First 5 seconds of the fire. And this is, I should have looked for the first 5 seconds. There's methanol in the equilibrium point. There's gasoline at the equilibrium point. Squish it. Maybe. Yeah. So the top one is gasoline, the bottom one is methanol. And the point that you can see qualitatively with your own eyes is that there seems to be a lot more radiant energy coming off that gasoline fire, the block of data at the top, than there is off the methanol fire, block of data at the bottom. And again, that's absolutely true. Notice the proportion of the UV to IR energy, really not that terribly different. They both have similar amounts. We took a look at, we noticed that the UV detection with the star logic, which requires a steady level of output at that 25 counts per second range, it took a long time to alarm, and one can now understand why that would be, because even averaged over a long period of time, quite only about 20 seconds. In fact, there must have been a momentary surge in the UV, as we saw the flickering. We talked about the oscillation that will occur around the peak output level once the equilibrium is reached, and that did allow it to be triggered. So again, this kind of data allows us to tell the customer, for example, they may say, well, I want to see square foot of gasoline, I can't get the detectors any closer than 50 feet away. What can I do about that? Well, we have a couple of choices for you. We know that we can switch technologies, the X3300, PM6M, or we could go in and say, well, we should run at a higher level of sensitivity. We know what the trade-offs are there. If those trade-offs are acceptable, we'd be able to provide not only qualitative advice, but quantitative advice.
Okay, we're going to do methane next.
Yep.
We want to put that which distance?
I was going to leave it here for purposes of comparison of the count data. The disadvantage to that is that most of the systems will be out of range, but it's easy and quick enough to do that we can probably just move it in and run another test with all the systems within range.
Okay. When we look at these fires, these are the fires that FM looks at and verifies the distance. So basically third-party evaluation. You will be what you say, commanders. We do list all the different fuels because it's important to be able to design to the right fuels.
And it is also, I should point out, having been through this recently, one can obtain FM certification of your performance as a flame detector with as little as one fuel. And then you can make additional claims in your manual that may or may not be substantiated by factor neutral certification. It's a fine point that you should be aware of, because it only takes testing with, say, gasoline to get the FM Diamond. It meets their minimum requirements. The FM standard 3260 for flame detector performance does not give a minimum level of performance, but rather checks your performance against what you claim in your manual, and you only need to verify one of the fuels that you claim performance with. So it's just something to be aware of. Okay, so we're going to be with the methane plume fire here at a distance of 50 feet, and I'm ready. Everybody else is. There's a fire that comes to equilibrium quite quickly. Of course, if that was a growing gas leak because the packing was burning away on a valve or something, it'd be a different story. Why don't you move that into 25 feet, Mr. Crosley?
If I can drive it.
In this particular case here, we see just what we'd expect. Most of the systems are beyond their sensitivity limit for this size fire at this distance. But we have response to the X3300 in 4.3 seconds. And I guess as you've seen this device, you notice that really never responds any quicker than 3 seconds. And that's inherent to its signal processing algorithm. It does a lot of advanced calculations to distinguish fires from non-fire sources of radiation. And it requires a sample of data in duration of about 3 to 6 seconds in order to make that determination. So it's inherently a slower responding device. But that's usually acceptable in situations where the high level of false line rejection is required. The unitized UBIR didn't manage to respond in 0.8 seconds. You might have noticed it was kind of toggling in and out. The only other detector that gave us a good solid response was the UV detector. And again, we see that there was some difference between the star logic and the standard version of the device. And again, you can see that the reason for that is just right at that point where just below the alarm threshold, so we're waiting for an occasional excursion in a higher intensity direction to get the UV detector to indicate alarm at this distance. Notice here that in contrast to the other two fires we've looked at, we have almost equal amounts of UV and IR. And that's just a property of this type of fire versus the other two fires that we looked at. And it's important to know that to make the best application of the technologies to the hazard in question. Now we move in here a little closer to where we would expect all the systems to alarm. This will also be the distance at which we look at some false alarm sources. So that'll minimize the amount of moving around we have to do. And I'm ready if you guys are.
We're actually still on range like 5 feet with a PM6. That's long range to heavy fuels, but very short range for light fuels.
Okay. Again, to illustrate the point that this particular detector won't detect given fire. It all depends on how close, how big a fire. Here we see everything responding in very short order, and my X3300 just made a liar out of me. As it gets more intense information, it's able to make a decision without quite so much calculating procrastination. So this is an exception. At 25 feet, we're at less than a quarter, or actually at a quarter of the detection of this device to this hazard, which means that we've got basically the inverse square law. That would mean we have 16 times the amount of radiation that we need for this detector to alarm. So, yes, that, when you go over 10 to 1 in terms of the amount of radiation you need, you can expect the detector to do a little better, and everything else is reacting in the amount of time that is typical to the minimum. The 7698E is, again, a device that at standard settings for TDSA is a 2.5, 3, 4 second type of response time. So again, this is something that we would consider as best case. We look at the, I must have ran out of overheads. Well, you'll have to take my word on this. The UV and IR output level here, now we have in the UV side of things about 90 counts per second, in the IR side of things 40 counts per second. So as you can see, we've maintained about the same proportions of UV to IR, and again, that's just something that one needs to know to correctly and optimally apply the technology to the hazard in question. So you can see all the detectors detect all the fighters at a given size or some distance. So how does one make a selection for the right detector for the job? And oftentimes it boils down to the interferences that might be present. I'm making an interference for you right now. 6 kilowatt radiant heater that's warming up over in the corner behind that rather strange looking apparatus. Now, there's infrared present right now. I can run the acquisition system. I don't see any infrared output. And the reason for that is there's no flicker. It's a steady source of infrared radiation. As we said before,
black box, is that what you would call black box or not?
black body type of radiation, gray body, black body, hot body, all roughly synonymous.
This would be what you normally would see like in a turbine enclosure. You may see this in a compressor module.
Plastic extruders.
Yeah, polypropylene extrusion, plastic molding. It can even be in hangars where they're doing metal treating with heat blankets and people working on it. Heat is used a lot more than you would think in an application, or byproducts are heating up to be clumped in pipes to look the same.
Right. A lot of different industrial processes are hot enough to produce radiant heat. But you can see that this radiant heat poses no threat, and the reason is there's no flicker. We talked about the IR detectors needing a level of intensity, which, believe me, we have, we'll see shortly, and the presence of flicker. We can add flicker to that source. Jeff, if we do that. See, we have U7698E without TDSA and alarm, and just to give you an idea of the level of intensity, I'm getting about 100 counts per second from that particular source, which is roughly twice what that methane fire produced at the same distance. So that's a very, in terms of the intensity of the fire, that's a very intense source, even though its radiant energy is not concentrated in the 4.4 micron band. It's spread over a large region of the IR. It's an intense enough source that even at that little slice of the 4.4 micron band that we're looking at, that actually is more intense than the methane fire that we previously looked at. Notice how the UV IR detectors don't respond. The IR detector half is getting plenty of IR, but there's no UV present. And most significantly, the X3300 and the PM6M, which use multiple wavelengths in the IR region, is able to distinguish the fact that that's a broadband IR emitter, black body, hot object IR emitter, and not an IR emission emitter fire. Now, before we shut that thing off, I think we better show one other thing. And that is when you think about this, the detector doesn't false alarm to this source, and that's good. You don't want false alarms. But we have to remember that it needs to retain its capability to generate an alarm to the fire even when this source is present. It's quite easy to make a detector that won't false alarm to a given source. It's more difficult to make a detector that can retain its ability to respond to fire even while rejecting a non-fire. After all, if you have a detector that simply is resistant to false alarms but gives up its ability to respond to fire, you've done nothing more than going over and turn the bypass switch. I like to call that strategy of detection systems auto bypass. Not really what we're after, I don't think. So, we could have the fan, and we'll do the gas and fire alarm with this. You might notice we have to think a little harder about this. But 276-980 PDSA, generating alarm.
Before we turn that off, why don't we just show what happens if you do get a mixture of IR and UV
Oh, good idea.
radiation. Can happen. This is where the multi-spectrum IR detector has an advantage. Move your hands at it.
Don't hurt yourself. Oh, good. Jeff's
Close enough where you can't get it.
Okay, so give us a nice steady blast. This is a high intensity UVR.
This would be like someone welding, arc welding.
Yeah, again, it's in that hanger application. Imagine they're using some heat treating blankets to preheat the structure that they're going to weld. And another part of the plane they're welding. So even though there's not a single source of UV and IR, there's concurrent sources of UV and IR possible. And it's, of course, that defeats the UV IR strategy, but it does nothing with the multi-wavelength. Okay, now low at start, this is the response time of the detectors with the current black body and the square foot gasoline fire. Notice that we did take a little longer to be able to make a computation to sort out and separate the signal from the fire versus the signal from the hot object. But both the X3300 and the 7698E with PDSA alarm. In this particular test, the PM6M didn't alarm. That hot object had been a little less intense. The result would have been different. Again, this is something that's not absolute, but a matter of degree. It's akin to trying to see firefly against the sun at some point. The level of IR from this gasoline fire at this distance is roughly about equal to that of the heater, is getting the same amount of IR off as the gasoline fire, which is a pretty aggressive situation, but one that I wanted to use to just demonstrate to you how good the X3300 is at being able to respond to a fire threat, even though it's actively rejecting a very, very intense non-fire source. Now we've got the UV arc fired up here. I'd like to demonstrate to you the utility of our star logic. Don't let Buff near that switch.
I used to just plug it on the wall and just go.
Not UL rated. Okay, We'll start with a nice steady blast of the UV, and I'll take an acquisition picture of it so we can look at the intensity level.
It doesn't look like very much. You would see arcs like that, say, in an electrostatic painting application where the grounding hooks start to follow the paint, and you start seeing arcs like that as that grounding is lost.
You can get a little close. That's a nice, it's actually a neon sign transformer. It's a nice purple arc. Back when we used to have more fun, it made a great, big, wonderful Jacob's ladder type of thing, like in Frankenstein's laboratory. And we're getting about 450 to 500 pounds per second out of this.
That compares to what for the fire resistance?
That compares to no fire, hardly at any distance. The only fire we've seen that got close to that level was the time zero detector a foot away from the spread of gasoline. So electric arcs are very intense sources of UV, and as you can see, an alarm is produced. Now,
I guess Rob, just one thing is that when you think of welding, that would be like a little spot welder. And really a welding, when I say go a couple miles, easily. We're looking at 25 pounds to go on most rows, and we're getting 400 pounds. A little bit. You know, when you get an arc, you weld it. That's off either UV.
yeah, we talked earlier about line of sight and that kind of thing. Well, one exception to line of sight is the way UV can scatter. You might be familiar from your elementary science days about how the scattering of UV in the upper atmosphere is what makes the sky blue. What scattering means is that the UV radiation, as it hits the different air molecules, kind of bounces around a little bit. And much like if you've ever seen a street light in a snowstorm, you see kind of how the whole snowy sky is lit up around that street light. Same thing happens with UV detection. There's a lot of scattering off the molecules of air that we have, much like you get scattered off those flakes of snow regularly. And a true story here is one day Jeff and I are doing testing down here and we're getting false alarms out of our UV detectors. It happened to be a nice day and we had the overhead door open. So finally I realized that I should go outside and think about it. When I did, I walking down the road and I noticed the two doors down inside their identical closet. One of our neighbors had one of the trucks inside and they were doing some welding repairs on it. So we had no line of sight, no direct line of sight whatsoever. It was going out, scattering around, back in here. It was a high enough level of UV to give me a false alarm. Now, that's not a mile away, but it's not within the path. I guess the point here is that you're going to have arc welding present for electric arcs in general. Except in a special circumstance, we're going to demonstrate for you, UV detection needs to be supplanted with either with UV-IR type of combination or another technology should be considered. Now, Star Logic allows you to use UV detection, and more important, UV-IR detection, in cases where arcing might just be an occasional occurrence. An example of this is electrostatic paint spraying, where a piece, normally they're connected to earth ground, and no charge can build up on the piece being painted, but as the hooks and the carrying equipment that's used in production becomes coated with paint, it becomes an insulator, and the piece being painted build charge up to a very high level. Then as it approaches a grounded object, the floor, what have you, somebody walking near it, you can give a momentary arc, and that not only can be a source of ignition, but if it isn't a source of ignition, it certainly is a momentary source of UV. What I'd like Jeff to do now is just give us a simulated transient arc with our fixture there, so we can watch the reaction of the U7602E standard without the Star Logic, that's the top position, versus the one with Star Logic. Go ahead, Jeff. Okay, so you see there, we've got a very high intensity level of UV. No amount of desensitizing the detector can hope to eliminate it from that alarm. Okay. Just impound it. Where was I? Oh yeah. No amount of desensitizing could eliminate that reaction to that arc. But the Star Logic is looking for not only a level of intensity, but we're also looking for a consistency of the output over a period of time. Specifically what we do is we divide time up into what we call gates. We want to see a minimum level of output in each one of those gates for a number of consecutive gates. This is an advanced signal processing algorithm that we've invented that allows you to use UV and UVIR detectors in areas that one would think would be completely unsuitable for that kind of technology. But again, it's not just the sensors you bring to bear on them, or the expertise you have applied them, but the signal processing algorithms
Who drove over the Sabre?
used to enhance the capabilities. I think that's all we really planned on covering tonight. If it wasn't enough, I know it's late. I do appreciate everybody taking the time to come out here. We'd be happy to answer any questions or light anything on fire that you'd like to see.
No, I'm not being on fire again.
You didn't mind last time. Buff used to have a full beard just several weeks ago. Now he's
My
down to
armor finally grew back. I can wear short sleeves again.
In all seriousness, if you come up against any application where it'd be helpful to see a given fuel burn, do you have any other questions? Only too happy to entertain that.
I was going to ask you about you mentioned about this bench job for this. Have you had any testing done in similar lines? Because those fires are unlike this thermoelectric fires.
Right, they tend to be, well actually it kind of depends what type of paint they're using. We've done a number of tests with various formulations of paint. We get them right from the people like Chrysler, GM, what have you, whatever they're really using. And we've burned them in a raw state, we've sprayed them on spray guns, we've burned them as they dry and giving them the flammable vapors are coming off, and it's not actually the paint that's burning, but the vapor cloud above the paint. And did you have a question beyond whether we've done that?
It's similar to that. Basically, I was going to ask you about this. Electronic components, they typically use the same kind of setting. Which as the object and the exhibiting are actually absorb the particles, spin particles. And there wasn't much research done, or actually I couldn't find anything that really stated that you should use this or UV or IR or combination, anything.
Yeah, I'm not really about, putting the epoxy coating and so forth down on electronic components.
Oh, we actually, the only epoxy applications we have some epoxy covered rebar where they coat it with epoxy and run it through a curing oven. And
typically that's what we call a powder coating operation where the paint is actually solid particles that are then fused under heat. We've done testing with that.
yeah, epoxy is burned very readily and typically under elevated heat.
Now, when you say you don't find anything published,
Yeah, because
you
I
don't
was
find anything published anywhere, because if we were to publish our results, it would be screwed as applying to all detectors and they're all equal. And if that were the case, we'd be only too happy to share it. But that isn't the case.
Yeah, you
Hating when you do that straight. We've, not only do we do the work that we're talking about so far down here, that we have to confess we get our competitors out and learn what their strengths and weaknesses are. But typically for that kind of application, I think most of the time we're using IR would work.
Well, it would depend on how, if it was a very, tight area, that would be an application. We'd probably use one of the fiber optic detectors. Being able to put the detecting sensor right next to where the source is going to be, so it's going to be very fine.
Yeah, I've never actually seen
I personally don't get involved with that much either. But if somebody does ask me, it's just like, no, I don't.
Yes, any questions on products, if this is going to be a good application for flame detection, give us a call. We have 4 or 5 different inside sales guys. I'm available. And we're here to basically make the fire detector with the suppression systems, and so that, add safety to industrial applications.
Anybody else?
Do you happen to have any of that fiber optic technology here that we could look at after we break up?
I don't want to hold everybody else.
Bring it back. There should be still a fiber down here. Oh, I don't have that here, man. No, I don't have one here.
Just asked us to bring it back.
Yeah, we could, but the fiber optic is very small. We look at a head that collects the energy that's about this big with a fiber that would go out to 100 feet. So
It looks kind of like SCAD tubing. If you've ever used the Ansel SCAD tubing, it's just a little kind of like about quarter-inch diameter thing. And you route it into the, typically I've seen it, I guess one place I've
go
seen
to
it
the
used-
cat track,
Yeah.
mount it under the overhead paint facilities. You have some information on that, Matt.
Yeah, yeah.
Thank you.
Okay.
Thank you very much.
Very welcome.